Alright, so I'm going to talk more about confidence intervals. There's one extra type of problem that we're going to do at the beginning, and then a lot of the rest of it is just another example and then just generally recap on confidence intervals and what they mean, because I know we all need more practice with that. So we're going to start with the new type of problem related to a confidence interval, but more specifically the margin of error. So in this type of problem, we know the margin of error we want. So in this case, we are trying to measure the proportion of adults who approve of attempt to clone humans, and we want to know what sample size we would need to be within 0.04, meaning we want our margin of error to be no bigger than 0.04 of the true proportion of adults who attempt to clone humans, and we know we want a 95% confidence interval. So when we talk about margin of error, the confidence level has to do with that, but also sample size has to do with that, because however big our sample size is going to impact how wide or narrow that standard deviation is. So remember, your margin of error is the stuff that comes after the plus minus in our confidence interval. So it's basically the z star, the critical value, times the standard deviation, which for proportions is the p, 1 minus p over n. Technically it's p hat because that's what we know on a confidence interval problem. And that's what our margin of error formula is. And so in this case, we know that we want a specific margin of error. We want that to be 0.04. I'm not going to worry about the plus minus because obviously when we actually calculate the interval, we'll do the plus minus. For this situation, it's okay to just leave it as positive. And then we also know that for a 95% confidence level, our z star is 1.96. So we don't know n, obviously, because that's what we're solving for. But in this case, we also don't know p or p hat or anything because we haven't even taken the sample yet. So of course we're not going to know the sample proportion if we haven't taken the sample yet. But we have to put something in for p, otherwise there's no way I can solve this problem. So what we do in statistics is we think about, okay, I want 0.04 to be the absolute largest margin of error that I could get no matter what happens in the actual sample. So to do that, I figure out what is the largest possible value I could get on the top of that fraction no matter what I plug in for p. So I'm going to go through some options. What if p was 0.1? 1 minus p would be 0.9, and the top of that fraction would be 0.09. That's not very big. I can probably get bigger than that. So what if p is 0.2? So 1 minus p would be 0.8, and that gives me 0.16. So we've gotten a little bit bigger, and the bigger our p hat gets, right, the bigger that value gets, if p is 0.5, the value on the top of that fraction would be 0.25. And then at that point, if p is 0.6, we're going back down. So 0.25 is the actual largest value I can get on the top of that fraction, which means if we want to make sure that 0.04 is the absolute largest margin of error that I'm going to get, and I don't actually know what p hat is, then this is what I should be using on the top of that fraction. That way, no matter what ends up happening in the real sample, I know that 0.04 is the absolute largest margin of error that I'm going to end up getting no matter what. So that is how I handle this type of problem. If I don't know what p hat is, or if I have no estimate whatsoever for what p could be, I'm going to use 0.5 so that the top of that fraction is the absolute largest value that we could get no matter what. So that's what I'm going to do here. I'm going to erase my extra lines here and make this look a little bit nicer. But on the top of that fraction, I'm using 0.5 for p or p hat. So 1 minus that is also 0.5. N is what I'm solving for, and then I want that to equal 0.04. From this point, it is algebra. Yay, algebra. A little bit of a complicated algebra step or process, but just to go through it, I'm going to start by dividing by 1.96. Right. That gets rid of that. The next step would be to square both sides to get rid of the square root. All right, that's going to leave me with, I'm going to go ahead and multiply 0.5 times 0.5 is 0.25 over n. equals this whole mess of a number. And then this is always where people tend to get a little confused, especially just in general with algebra. N is in the bottom of a fraction. I cannot solve for n if n is in the bottom of a fraction. So I need to multiply by n to get it out of the denominator. And then to solve, I'm basically dividing by this crazy number here that's on the right side of the equation. Now, in terms of actually figuring out what that equals, there are several different ways that I can do that in my calculator, but one way is to do it step by step. My suggestion, if you're doing it step by step, is to make sure that you are not rounding in between. So if you're doing it step by step and the first thing you do is you divide 0.04 by 1.96, and the next step when you square it, right, don't round that value. Right, your calculator, if you just hit squared, it'll know to take that last answer and square it. But you can also get to that answer, the A and S, by doing second negative, and that will put an answer. That'll help with the next step, because the next step was to divide 0.25 by that number. So 0.25 divided by, and then you could do second negative to get the little A and S, and then there you go. Now I could also get that same answer by just doing the entire math at the very end using what we have here. So 0.25 divided by parentheses 0.04 divided by 1.96 close parentheses squared gives me the same answer. So either way, when I do that, I get an answer of 600.25. So n is 600.25. Now obviously I cannot talk to 0.25 of a person. That doesn't make sense. But remember, we're thinking worst case scenario. We want no matter what for 0.04 to be the absolute largest margin of error I could get. If I talk to 600 people, I could end up with a margin of error that is slightly too big. The bigger the sample size, or the smaller sample size, the bigger the margin of error. So I could end up with a margin of error that is slightly over what I wanted. So on this type of problem, when we're talking about what is the absolute sample size that I could absolutely use and get 0.04, I always round up. So even in regular rounding rules tell me to round down, and this type of problem I am always going to round up. That way I'm guaranteed to get the margin of error that I actually wanted. So let's do another example of that same thing. With this one, it says according to an article in the Chicago Tribune, about 75% of all high school students owned a cell phone in 2010. It is reasonable to believe that since that time the proportion has increased. I think that's a very reasonable assumption. So suppose we wish to conduct a survey to determine the current proportion of high school students who have cell phones. We want to be within 6%, and we want 90% confidence, and we're going to find the necessary sample size. So, same idea, right? My z-star for 90% is 1.645. We have square root of p times 1 minus p over n. N is obviously what we're solving for. I'm going to come back and talk about p. And then we want that to equal 6%. Make sure you turn that into a decimal. If you use 6 as that number over here, you're going to get a number that is really, really ridiculously small. Basically, you're telling the problem, the formula, that you want to be within 600%, which is crazy. All right, so in terms of p, now normally we would use 0.5 if we had no clue what p or p hat might be. Now in this case, we have a previous number, which is 75%. Now it's not always necessarily safe to use that number in the worst case scenario, but in this case it is, because our idea is that the proportion is increased, right? 0.75 times 0.25 is 0.1875. All right, we think that proportion has increased, maybe to 0.95. 0.95 times 0.05 is an even bigger number. Just kidding, it's an even, wait, hold on. I'm going to find out what it actually is. Sorry, it's an even smaller number, I said that backwards. And remember, our goal is to make the top of that fraction as big as it can possibly be. We don't think it's going to get any bigger than that. We think if anything it's going to get smaller as p gets bigger. So I think I'm going to go ahead and just put 0.1875, but we got that by doing 0.75 times 0.25. So in other words, if a problem gives you an estimate and we think that estimate has probably increased, we think our true p hat is actually bigger than that, it is safe to use that value as p. Now usually a problem on my test, on AP exams, they will kind of give you a hint whether they want you to use a given value or just use 0.5. Like they'll tell you, like, hey, use the estimate that we had as p in this problem. They'll try to make it a little bit more clear. All right, so now we're doing the algebra. So just like before, I'm going to start by dividing by 1.645. To get rid of that, I'm going to square both sides to get rid of the square root. And then I end up basically with 0.1875 divided by this entire crazy number. When I do my calculations, right, I end up with a value of 140.9. Again, depending on how you did it in your calculator, right? I kind of showed both steps again in both ways, but we can do it all at once. Either way, so 140.9, which again, we always round up. It makes sense to round up here. We would normally round up, but in this case, we would anyway, because we want to make sure that 0.06 is the absolute biggest margin of error that we get. And that is how we do that kind of problem. So when we're looking for sample size based on a specific margin of error, that is what we need to do. Right. I'm going to do another video where I go through examples of confidence intervals and just give you more things to think about in terms of how we interpret them. But that will be another video, so be on the lookout for that.